like I was saying, we have to study this curve, and at the end, we are required to state the function whose curve is represented as you can see. We study this function. At the end of studying this function, we state the function whose curve is represented as you can see on the screen. Is that understood? Yes, Rodrigo, can speak. Speak. Okay, it's taking its time.
Yes,
Yes, equation. Let me change my position. My position is changed for the minute. So let us start by looking for the domain of definition of this curve. So looking at this curve, what is the domain of definition of this curve?
X number 1.
So the domain equals the set of all real numbers from negative infinity to 1 from below, then 1 from above to positive infinity. Positive infinity. This question is relatively easy. Now the next thing, let us look for the limits. Let me call this function y. What's the limit as x tends to negative infinity?
Negative infinity.
Negative infinity, because you can see this is moving to negative infinity. And you continue to move, so it's negative infinity. And what is the limit as x tends to 1 from below?
It's still negative infinity.
Yeah, it's still negative infinity. You can see this is 1 from below. It's moving to negative infinity. So this question is just the same like the previous one. The limit as x tends to 1 from above.
It's positive infinity.
Yeah, this is it. It's moving to positive infinity. 1 from above is going upwards. So that gives us positive infinity. And the limit as x tends to positive infinity.
It's still positive infinity.
Positive infinity. I'm not getting the voices of the other guys. Are they actually in this class? Or because I said nobody should? So that's it for limits. Now let us look for the asymptotes. What is the vertical asymptote? The equation of the vertical asymptote.
X equals 1.
X is equal to 1. All right. Do we have a horizontal asymptote?
No.
But we are very sure that we have an oblique asymptote, right?
Yes, sir.
So what's the equation of the oblique asymptote?
I need to determine it.
But we are going to determine it. So we have to determine it. Now we know that since this oblique asymptote is a line, we can write this oblique asymptote to be of the form OA to be y is equal to AX plus B. Because that's the form for oblique asymptotes, right?
Yes, sir.
AX plus B, and we can determine the values of this A and B. Now we can determine these values. Let us look at this curve. We are focused on the oblique asymptote. Look at it very well. With this oblique asymptote, there is an intercept here. When x is 0, y is minus 1. Can you see that?
Yes, sir.
At this point.
yes.
So we can see that value when x is 0, y is minus 1. So you have minus 1 to be equal to 0 times x is 0 plus b. So we already have the value of b now.
Yes, sir.
So b is equal to minus 1. Now we need to look for a. We look at another intercept again for that oblique asymptote. This oblique asymptote also passes at this point. Can you see when x is 1, y is 0? Can you see this point? It passes here also. Though it's the center of the curve, yes, it also passes there. So when x is 1, y is 0. So we fit it there. We'll have 0 is equal to 1 times a is a now. I'm sorry,
Yes.
1 times a is a. So this will be equal to a. Then we know the value of b to be -1. A plus -1. So what's the value of a?
It is 1.
Yeah, so a is equal to 1. So what's the equation of our oblique asymptote? It is y is equal to what?
X plus minus b
X minus, and b is -1, right? So x
minus 1.
1. So this is the equation of our oblique asymptote. I love this question. Now we can equally get the intercepts. Let me call the intercepts A and B. For the intercepts, we have the point A. The intercepts are clear here. We have just one intercept, this one. X is 0, y is -2. Can you see that? So we have the point 0, comma, -2. That's the only intercept that we have. Now I think we have all that we need. We can equally, they can give us this question and say we should make the variation table. Let us just make the variation table so that we can now look for the function itself. So let us look for the get the variation table. Now, I skip something. The turning points first. The turning points. We have two turning points. You know the turning points at x. Who is going to PP now? 0.22. You can see this turning point here now. 22. And this another turning point here. X is 0, y is -2. Let's call that one y. 0 minus 2. 0 minus 2. So let us get a relation table now. So this relation table, we have x. Then we have negative infinity. We have a vertical asymptote, but before this vertical asymptote, we have a turning point. And the x value at that turning point is 0. So we have 0 at the turning point. Then we have the vertical asymptote of 1. We have another turning point when x is equal to 2. Then we have positive infinity. Oh my god. Positive infinity. All right, so this is what we have the x values. Now the gradient function y prime. Since this one is a vertical asymptote, I'm going to put a double bar lines here. X equals 1. Then this gradient function, this is a turning point, so this value here is 0. And this is another turning point. The gradient function is always 0 at the turning point. The gradient is always 0 at the turning point. So let me use broken lines to show that it's a turning point like this. And this one should be the same thing. Now let us get the signs. Now for this function from negative infinity to 0, what's happening? This from negative infinity to 0, look at the curve. It's increasing now. It's going up. Can you see?
Okay.
From negative infinity, the curve is going up. You're climbing here. So it's positive. Then from 0 to 1, cutting from 0 to 1, we are now going down, right?
Yes.
Yeah.
So we're going down, so it's decreasing. Now from 1 to 2, from 1 to 2, 1 to 2 is a region, it's the same. From 1 to 2, it is going down. is descending. Once 2 is descending or reducing, and from 2 to positive infinity, this is 2 to positive infinity, the curve is going up rapidly.
It's going up.
It's positive. So from here now, let us get the values of y corresponding values. This one is positive. So it's increasing. Here it's negative. It is decreasing. Negative again. It's decreasing. Here it's positive. It's increasing. So let us start with the first one. At x equals negative infinity, the limits of negative infinity was negative infinity. And increasing from negative infinity. When x equals 0, this is the turning point. We have the value of y to be 2. This is the turning point here. So it increases to negative 2. Then from 2, it decreases to negative infinity. That's what you can see here. Or the limit as x tends to 1 from below. It's negative infinity. Then 1 from above. The limit was positive infinity. Since the turning point. So the same. Then decreases to. Now when x equals 2, this is the turning point. When x is 2, y is also 2. So it decreases to this turning point 2. That's what we see here. Then it increases again from this point 2 to positive infinity. To positive infinity. So now, how can we obtain the curve of this function? The curve can be obtained by saying y is equal to the oblique asymptote plus a constant, let us call it c, all over, according to this curve, x should not be equal to 1. So x minus 1 for x minus 1 here. This is how this curve will look like. And this will be equal to, for the oblique asymptote, how can we get it? We already have it.
This x minus 1.
So x minus 1 plus a constant all this over x minus 1. Wow. This x minus 1 here is the vertical asymptote. Why this x minus 1 here is the oblique asymptote? Now we need to look at the value of c. To look at this value of c, we need to use any intercept that this curve has. Any intercept. We have an intercept. This turning point says an intercept now.
Yes, sir.
That's where we're going to use it. It's a turning point, both a turning point and an intercept. So when x equals 0, what's the value of y? Y will be equal to negative 2. So what does this imply? This implies negative 2 should be equal to x equals to 0. So I have negative 1. 0 minus 1 is minus 1 plus c over 0 minus 1 is minus 1. So when you solve this equation, what will be the value of c? Solve and tell me. C will be equal to
negative 2.
C what?
C equals to 1.
Yeah, C will be equal to 1. So therefore, we graph into the graph of x minus 1 plus c over x minus 1. But my c now is equal to 1. So I'm going to replace it with 1 And this is the curve of this. This is the function that we have sketched before. So this is this question. Are there any questions on this?
Nonsense.
I like this question. Hello, pilots. In the 1J pilots, how are you today? Can you put on your microphone? In the 1J pilots. Hello. Oh, I don't know if it's on the mic. Right, guys. Good. Let me clean the bottom and look at the next one. Oh, somebody wants to
So
play.
if we are just given a variation table and asked to look for x1 y is equals to 0, or to look for x1 y is greater than 0, something like that.
If you're just giving the variation, please take a question again.
If the function was given as a variation table and you are asked to look for x when y is equals to 0, I mean when the function itself is equals to 0 or greater than 0, something of that nature.
Yes, I'm thinking of questions like that because they can give you a variation table and say if you sketch the curve and come out with the function, all of that, right?
Yes, sir.
Now, when they give a question like that, if this one has an oblique asymptote, right? They'll need to give you further information about the curve. Is that okay? But if it has no oblique asymptote, then you can get the curve
Yes.
directly from the variation table. But if it has an oblique asymptote, they will give one line again that given that x is equal to this and y is equal to this, so that you can get the values of the constant in and come out of the function. Otherwise, you stop with the constant at the end. You can still solve, but you have a constant in your answer, which is not equal to two. You have a question of that in front of you.
Yes, sir.
All right, can you snap and send to the group?
Okay.
All right, that is good. So our next question of today is this one. Beautiful question two. In the last class, right, we look at a function like this. It was just lame. Something was of this nature, right? But this x was not there. This x plus was not there. And secondly, the function did not have this absolute value sign. So can we look at this function?
Yes, sir.
Right. I hope there are students for advanced level technical here too. Are you there?
So we're not getting you.
Are there any advanced level technical students besides Rodrick now in class? All right, nobody is saying anything. So let's look at this function. Normally, the idea to follow to sketch all functions is the same. But logarithmic functions have some particular behavior and exponential functions have some particular behavior. And then there are equally some characteristics when oblique asymptotes come in. Now, to split this function, what is the domain of this function? I'm going to skip so many things. I'm not writing much since we already have the basic concepts. So what is the domain?
So all real numbers except 1.
That's a very big chart. Huh? Now there are two parts of this function. Look at this part. If you consider only this part, the domain is a set of all real numbers. So this part is not our problem. The problem is the second part. So this second part, let us see. This second part will be defined if what we have, since there's an absolute value now, whenever there's the absolute value, this one will be defined. Because we put a negative number here, no problem, the absolute value will convert it. So this one will be defined if this x plus 1 all over x minus 1, the last function we did on logarithm did not have absolute value. So I'm taking this function because it has absolute value. So the condition of this function is defined is that this value should not be equal to 0. Because if this is equal to 0, half being 0 will not be defined. So this should not be equal to 0. And what are the two conditions for this not to be equal to 0? X should not be equal to -1, right?
Yes, sir.
And this other one, X should not also be equal to 1 now.
Yes, sir.
Now, this second one, like this, many students will not understand it. And students, this is what students usually face so much. X should not be 1. This one here is explained as follows. If X is equal to 1 here, we will have a number divided by infinity. And any number divided by infinity, any constant divided by infinity is equal to 0, right?
Yes,
So
sir.
we are going to have in 0, which should not be defined. So these are the two things that will help us to get the domain now of this function. X should not be equal to 1, and X should not be equal to -1. So the set of all real numbers, excluding 1 and -1, or we can say -1 and 1, excluding -1 and 1. This therefore already tells us that these two values are asymptotic values, right?
Yes, sir.
And so one of these will be equal to, let me clean these things now. So the domain will be equal to the set of all real numbers. So from negative infinity, -1 union -1 to +1. Oh, I love this function. Union. But you know the type of things that I like now. Union 1 or +1 to +infinity. So this is the domain of this function. -1 to 1, 1 to 1. Sorry, negative infinity to -1, -1 to +1, and +1 to +infinity. Now let's get the limits. Now the limit at negative infinity will be equal to, now see how you get the limit of this function. Is the limit of this first part of this function plus the limit of the other part. This first limit here will give us negative infinity. Now the limit of this one as x tends to negative infinity, we know that is a rational function. So just take highest divided by highest, highest degree divided by highest degree. That gives us x divided by x, which is 1, and then 1 is 0. So we'll have negative infinity plus 0. That's equals to negative infinity now.
Yes, sir.
So the limit here is negative infinity. In fact, if you look at this function, you see that this line y equals x is the oblique asymptote. So all the limits will be infinity. Then the limit at positive infinity
No, positive infinity.
Yes, positive infinity of y is of admitted y there. Will also be positive infinity because we are going to have positive infinity plus 0, which will be positive infinity. The limit is as x tends to -1 from below. -1 from below. So let's take the number -1 from below. This will be equal to, and let me see, we have -2. You know the limit is already infinity, right? And then here, x tends to -1 from below. Let's take -2 as in. -2 plus 1 is going to give us -1. And -2 minus 1 is going to give us -3, right?
Yes, sir.
-1 divided by -3 is equal to 1/3. And the ln of a number that is less than 1 the absolute value of this will be 1 on 3, which is the same as negative ln 3. So we have negative ln 3 plus minus 2. So this limit is going to be equal to negative infinity because you know that we are taking the limit at an asymptote. Then we take the limit at minus 1 from
So
above.
please, I've not understood that step.
My friend, you already know that the limit here is negative infinity, right? You know that, right?
So
Yes. The limit as x tends to negative 1. Look at it from the domain of definition. X should not be equal to negative 1, right?
yes,
Since x should not be equal to negative 1, it means that the function is not defined when x is 1, right?
yes,
Therefore means that the limit, if you take the limit as x tends to 1, it will be infinity. But that limit has two behaviors. It has a behavior from below that's almost like at the 1.9 minus 1.1 comes exactly before minus 1. And it has a different behavior exactly after minus 1. For example, this is a curve. You want to know that it's behaving like this or like this. So is it moving to infinity? Because this point, the curve is not defined here at minus 1. So we know the limit of x tends to minus 1 is infinity. But what we are doing now here is we are testing the sign of the infinity. Use any number to test. That's very close to 1 from below and from above. Is that okay now?
yes,
So we want to test. We already know the limit is negative infinity because the domain is telling us that x should not be negative 1. And it's also telling that x should not be 1. Whenever the limit is telling us that x should not be this number, it means that number is a vertical asymptote. So here we have as x tends to negative 1 from below, take a number slightly less than negative 1, like minus 1.1, and test in the function. You can take minus 2. If your final answer gives you a negative number, then the limit is negative infinity. Here, we take a number greater than minus 1, slightly greater than minus 1, we test. We take minus 0.1, this one will be positive. Minus 0.1 is going to give us minutes. So we can take, let me just take 0. Let's see like that. But this one now is dangerous to take 0 because this curve will have a funny behavior between minus 1 and 1. So 0 is not very good because it can mislead us. Let's take a number slightly greater than minus 1. Slightly greater than minus 1, you can have minus 0.9. So minus 0.9 plus 1 is equal to 0.1 over minus 0.9 minus 1 over minus 1.9. When we take the absolute value, all of this is going to be positive. Now plus, so the number that we used here was a number slightly greater than minus 1 plus minus 0.9. 0.9. Now with this limit again, it's going to give us minus
infinity.
yes, minus 1.9 minus this, and all of this is going to give us negative infinity. So I'll just showing how they do this thing. You really like negative infinity. Then the limit as
Yes,
x
sir.
tends to, the next one is as x tends to 1 from below. The limit y as x tends to 1 from below will be equal to, you can use 0.9 here and test. So that will be equal to 0.9 plus ln. So how 1 plus 0.9 is 1.9 minus this. The number is going to be greater than 1. So this gives us a limit of a positive number which is greater than 1, which is at the end we have positive infinity to the limit. Then we take the limit of y as y tends to 1 now from above. So this will be equal to, even one from above, we are still going to have positive infinity. And then the limit as x tends to positive infinity. Positive infinity will be the same as the limit at negative infinity, because all of this will just give us the 1, which is 0, plus positive infinity. This will be equal to positive infinity. You can look at past tutorials on limits that we did, or past lessons on limits. We did all of these things in the previous classes. So these are all the limits that we have. The next thing now, we're going to be looking for the asymptotes. So what is the vertical asymptote here? We have two
One
vertical
was
asymptotes.
negative 1 and 1.
The x equals to negative 1.
And x equals to 1.
And before you have x is equal to 1. Is there an oblique asymptote? No. But you have, yes, I'm sorry, but we don't have an horizontal asymptote. So oblique asymptote here will be the line y is equal to x now.
Yes, sir.
Yes, y is equal to x, because as x tends to infinity, all of this one will tend to 0. All of this tends to 0. If there was a constant like 2, then we consider it. Because x tends to infinity, this one tends to x over x is 1, then 1 is 0. So our oblique asymptote here is the line y is equal to x. Now the intercept. Okay, the intercepts. So if x is equal to 0, what will y be? Y will be equal to, so you have 0 plus 1 is 1 over.
So it will be 0.
So we have the 1 is 0.
Y will be 0.
So y will be 0. So it means that we have the origin 0, 0 to be an intercept. This exactly one is showing us that if we have used the 0 in testing here, that misled us. Whenever you have linear functions and exponential functions, and you want to test the limits, use a number that is slightly less than the value. Like here, number that is slightly less than negative 1. From above, take like minus 0.9. From below, take like minus 1.1. Always use that point something. Because at advanced level now, the limit is different, unlike the other functions that we at the other levels. Now we can get the gradient function y prime. So y prime will be equal to, these are two functions. I'll differentiate the first function x. Differentiate x, I'll have 1 plus, when you differentiate this linear function here, what are we going to have? The derivative of the core divided by the core, right?
Yes, sir.
Yes, sir.
The derivative of this core is bottom constant x minus 1 differentiate top. So x minus 1 differentiate the top, you just have 1 minus the top constant, now differentiate the bottom, plus x minus 1 which the bottom you have 1. All this on the bottom square. All this on x minus 1 squared. Now divided by the core. So divided by the core here is x plus 1 over x minus 1. So to divide it, I can just instead multiply by the reciprocal. Any way you do it, you have the same answer, okay? So don't bother. X minus 1. So I'm multiplying by the reciprocal, that's the same as dividing. And x plus 1. X plus 1. So finally, the given function I'm going to have 1.
So why is it divided by the core again?
That is how they differentiate logarithmic functions. The derivative of the core divided by the core.
Okay.
Look at our
Yes, sir.
past lessons, you see it very okay. So now this one will cancel out one of these ones. And here I have x minus x will be 0. And let me see, it's not 0 here. bottom constant divided by top minus top constant. So this x plus 1. So I have minus 1 minus 1. So minus 2 over x minus 1. So this gives me x minus 1 times x plus 1. If I just write x squared, because the difference of two squares, x squared minus 1. So if I simplify this function, look at the LCM, I have x squared minus 1 minus 2
Minus 2.
x squared minus 3
Hold on, x squared minus 1.
and x squared minus 1. So this is the gradient function. You can look at the turning point by solving the equation y prime is equal to 0.
0.
When we solve this equation, we imply that x is equal to what? Plus, this is already inherent there like that, or minus root 3, right?
Yes, sir.
Okay, so you can now look for y of plus root 3 and y of minus root 3. So you can do this one. So what will be y of root 3? Let's get the value of y is equal to root 3. All right, this thing. All right, give me a moment. Let me adjust something if I come back to class, okay? Please just give me 2 minutes, okay?
Yes, sir.
Okay, sir.
Okay. This thing.